In the meantime, any questions, complaints, remarks? How many people? Yes?
Well, I didn't attend the last class and I wanted to look at the lecture, but...
And it's not been online yet.
Yeah.
Woo! I'll book you online today sometime. Okay, we'll work on that. Slow processing. Yes?
What about the homework?
Yesterday. They grade them within 1 minute usually. It just goes into a computer. It counts the number of strokes vertically and horizontally. It takes a moment, okay? You need to give them time. They have to look at this. It takes usually a week or two to get it out.
Now that the homework is passed, can you explain about not one sheet about the and the map?
You mean how to do pseudo inverses?
No, I mean the interpretation of like geometrically and.
Can I defer that a little bit since we actually talk about this in class? We'll get into this in more detail, all those interpretations. Actually, partially today, mostly. Okay, someone is drilling. So let's get started. Welcome. How many? You're supposed to be 64 people. It means each of you counts 3 most likely. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, each of you is worth 3 people. It means all of you who are here now get a AAA grade. How about that? That would make my attendance so much easier. But it's okay. I don't care. Actually, I like the people who actually come. So, what did we do? Robotics. Drilling in the ceiling. Brilliant. We did the last time forward kinematics. So we did something which essentially allows us to compute f of q. The vector x of some point in space is a function of the generalized coordinates. So that's what people in robotics really like to call these things, generalized coordinates. Since as we discussed, you can pick coordinates as you wish. You just need to be consistent. So it should be generalized, so some coordinates, some degrees of freedom, which basically describe your robot, how it can move. It may be, again, prismatic, or it may be revolute joints. And it should be minimal. So you should not try to describe something with too many variables. You will run into trouble when you do that. So a 2-joint robot arm will be described with 2 variables, and you're done. So just as an aside, so people love to use the variable q for joint angles. The book likes that strange theta, or I like sometimes this theta. All the same, so just a placeholder for saying these are variables. Usually these are all vectors. If I wanted to make this super precise, except that I don't want to do this in the whiteboard all the time, it's too painful. With the slides and in the book, it should be consistent. Okay. What we stopped with last time was the interesting insight. If you take a 2-joint arm as an example, so here is a 2-joint arm, my favorite super trivial little example in an XY space. And if you look simultaneously at its joint space, let's call this theta 1 and theta 2, the joint space is just a simple box which is as big as the range of motion of this thing is big. So it has a max and min for every degree of freedom, that's it. But when you map this movement which you can do in joint space to this robot arm, it becomes this kind of convoluted weird space, and I just make it up right now. So this mapping is a pain. And that is actually one of the topics which people all the time kind of struggle with and get annoyed with. And you want to plan something in the external world, which is really what we care about. Since that's where we do manipulation. It's very hard to think in terms of joint spaces. Then how do you plan in this world so that you can guarantee that you can realize it within the space which you are here? It's very easy as you can think to plan a movement of the robot from here to there, which is partially not feasible. And that is so, you will see in many papers, in many robots, particularly actually these days, it's kind of fun. We're working increasingly with more complicated robots, like humanoid robots. And they have these kind of inverse kinematics errors. So infeasibility that you cannot reach certain points in workspace quite quickly, because they're very complicated. They're not easy to understand. Industrial robots were often built to be super simple in terms of their inverse kinematics. That means they create the robot configuration such that the workspace maps relatively easily to the joint space. But that's not the case anymore. Modern robots don't have that, and that's kind of the fun part. And what we're going to talk about today is essentially this topic of inverse kinematics. And it's a long topic. We could talk about this for many weeks if you wanted to, if you really want to go into methods. I'll just show you the basics. And with the basics, you can already solve 90% of the cases, except the interesting cases become more complicated. What is interesting? Okay, I want to reach from here to there, but that's not it. I might want to reach from here to there, taking certain constraints into account, like that I have some friction constraints at the fingertip when I reach there, or that I want to avoid that I hit into the end of range of motion of my joint. Then things become a little bit more complicated. And I will just mention that in the end, whatever we're doing today can often be solved with convex optimization approaches as well. And they allow you to add inequality constraints. Who knows about convex optimization? Yeehaw! Brilliant. Okay, 1, 2, fine, at least a few. Okay. It's very simple. Convex optimization is mostly if you want to have a simple story about this. If you have a quadratic ball and want to find the minimum, that you can do with the Newton method. So that's an optimization method, how to basically find a minimum in a function. And essentially, convex optimization is kind of the generalization of that. If you can formulate the world such that essentially everything is quadratic balls with constraints. Constraints are simple constraints, which are inequality constraints or equality constraints. And you've got to make sure that certain conditions are fulfilled. Then you can very, very rapidly optimize and find an optimum, a minimum solution. And what actually the important story today is going to be is that whatever we're doing when it comes to inverse kinematics has actually an interpretation of them in terms of optimization. And that is actually where this connection is made. And if you know this, stop doing this. If you know this connection to optimization, then you can actually at least get the idea that you can reformulate everything as an optimization problem. So let's get going on this and see what happens. Okay. Simple setup. Direct kinematics, x is a function of the joint angles. Inverse kinematics, people write it like f-1, an inverted function of x, except that this is not a linear algebra inverse operator. This is just meaning you invert the function. Whether you can know how to do that, whether you can do it analytically is totally unclear. And so what are the problems of inverse kinematics? So let's go through them one by one. Multiple solutions. That's a very simple thing which we'll demonstrate. Again, my little favorite two-joint arm, sitting here and reaching for a target which we make put here. Target. Okay. Now, if this arm has an appropriate range of motion, there is this second solution, which looks like this. So that is the second solution branch. There is no continuity between these two solutions. If I basically move this arm over here, then this end effector will go up, and then it will go down again. But there's two separate solutions. So this means it's the topic of multiple solutions. It means someone needs to pick at some point. And you need to have a criteria. First, you need to detect there are multiple solutions. Second, you need to pick then one which is more suitable. Second one, infinitely many solutions. That's also easily shown. Let's do the same game again. Now, I give you my target here. And in a brilliant move, I make this a multi-degree of freedom planar line, which looks like this. Now, what you can imagine is that this thing, this target, I can most likely, pardon my miserable drawing skills, most likely. I think it would most likely, okay, fine, like this. You might be able to reach it to it. Okay, my link lengths have changed a little bit, but that's how. And I can find another one over there. In essence, that is really, I can show to you, I'm now at this target. Let's say find solution to reach this target. And here's now my infinity of solutions. I can do a little dance for you. And these are all valid solutions. And you can see that even that I'm living on a continuum of solutions, there's an infinity of solutions. So now you need to figure out which one to pick. How do you resolve redundancy? And all your bodies are solidly redundant. Okay, we have 7 degrees of freedom in our arms, and another whatever degrees of freedom, 20 in your fingers potentially, and your entire body on top of that. So you are operating, say, with about 50 to 100 degrees of freedom all the time, and somehow you figure out how to use them appropriately. Actually, all of you will do this kind of very similarly, as people found out in behavioral sciences. No solutions is easy, okay? If I ask you to reach out here, which is now outside of what people can see, you have to go out here, that's most likely beyond what you can reach, so there's no solution available. But we also saw more complicated things, like in the two-joint arm, where you have one link which is long, one link which is short. There's something which is actually should be nicely in the workspace of the arm, like this target here. It's totally not reachable. You have that little midget arm here in front of that, can't reach it anymore. You need a big arm to get there. Last thing is getting this inverse function where we would like to get theta equals f minus 1 of x. Getting this inverse function analytically most of the time doesn't work. Pretty much in 99.9% of all times. We'll go through an example where it works just to give you the feel for what it's like, but most of the time it doesn't work. So you need actually iterative solution methods how to find that. Which iterative solution methods? What you do when you're iterating, there must be a criterion how you check that you're getting better, which already connects again to optimization. Good. So let's go through basically the basics of what we can do. Let's start one time with analytical solutions, despite they are the exception, and look at it how this works looks like. So you would essentially need to try to look at the arm and from the geometry of the arm, try to enumerate all possible ways how the arm could be configured, and enumerate all solutions which are there. Let's do this as one little example with a two-joint arm. And the book has that, and I just have it on the next slide. And we'll just try to develop this, how this works. So, beautiful slide. So we have an arm here. Again, boring two-joint arm reaching somewhere out there. We need a coordinate system. In this case, it is x pointing down, y pointing over there. And we need some link lengths. So it's all about triangle geometry, as you will see in a second, L1, L2. We need a definition of joint angle. So this here is called theta 1. And in the old tradition, we do the other one relative. So this is theta 2. Okay, good. And what we want is we want to figure out for a particular point x, y in space, like where we are right now, what are the joint angles to get us there? Okay, so that's as usually an entertaining enterprise. So how do we do that? So let me get the joint axis all the way out. So I want to figure out for a particular y and the particular x. So this is given x and y. How do I get there? Fine. Triangle geometry. What can we do in order to get there? We need to figure out these two angles. What can we do as a first step? Let me see. Oh, fine. This is the forward kinematics written down, but we've done this before, so I'm not going to this. So let's just start with something which is easy to determine. So we basically close this triangle. So this is actually a useful triangle to look at this complete triangle. And one of the first things we can determine is the length L. That means the distance from here to there. So this one we can call L. And then L equals simply the square root of x squared plus y squared. I hope this is correct. Good. Point 1. Then the next thing, you know this, what is it called? This, the law of cosines, I believe, in English. You know that one? Who knows it? All of you? Who does not know it? You don't dare not to know it? You can't dare not to know it. But it's just a little thing. So let me take this away. Essentially what it says, in general, if you have a triangle, which has an angle alpha here, and you have this here, then A, B, and C, you can always say C squared equals A squared plus B squared minus 2AB cosine alpha. Okay? That's the rule. You can apply this to any angle in the triangle, which is called. That's exactly what we're going to apply now. So basically, we can, for instance, say L2 equals L1 plus L2. So let me go back to the picture here. I can use color, but it's not very visible. So we say L2 this here, this line, is L1 squared plus L squared, and then the cosine gamma. So this here is my angle, which I now call gamma. Okay? This way I can figure out this angle, which is nice. So you get gamma just resolved. I don't have to do this, I assume. And the next thing what I do, I look for some angle epsilon. Where's epsilon? Where's epsilon in this plot? Don't see an epsilon. Fine. Epsilon is y over x. Cool. So y over x is basically this angle. I don't have this in there. Must have popped out at some point. So this here is epsilon. Okay? Y over x is going to be the tan epsilon. So good. Now, the cool thing is I can determine gamma. I can determine epsilon. That means theta 1 has to be epsilon minus gamma. Happy? Everybody happy? I hope I have that somewhere. So this is basically this arc term thing minus gamma. Perfect. And we can do the same thing now, basically having these determined. We can try to get a handle of this angle. What we have to do for that is, for instance, we use the triangle equality to figure out this angle here. Okay? And then we know that this angle plus this angle has to be 180 degrees. Actually, line of the law of cosine, not triangle equality. Line of cosine, I get this angle. From that one, I can do 180 degrees minus this angle gives me theta 2. There's many ways how to do this. It's all about triangle geometry. Good. So that was relatively straightforward. And obviously, it's a super simple triangle. Okay? This is as simple as it relates to that. Now, imagine you do this in a 3D space. You're basically all the time imagining yourself wandering around the robot and trying to figure out how it's configured. It's a huge pain. And frequently, you can simply not solve it. You cannot find appropriate triangles which you can solve. Good. And that's then when we have to go to iterative solutions. Cool. And this is actually an important topic. We're going to something now which is called differential kinematics. And it's a very useful topic to know about. I need here blue again. So we have our original x, no, without a dot, x equals f of theta. So this is the direct kinematics. What I'm going to do now is I take the first derivative. So this is x dot with respect to time. And then this is, if you remember, df d theta times d, oops, okay. So partial, but then absolute d theta dt. Okay? So at the whiteboard, this is the Jacobian, which is a function of theta, times theta dot. So what does that tell us? Well, interestingly, this tells us now basically how to relate a velocity in joint space to a velocity in Cartesian space. Again, my little favorite multi-degree of freedom arm. So if I'm here and I want to move in this direction with x dot, this tells me what is the theta dot which will realize this x dot. So that's useful. It tells me how to move in order to go into a particular direction. Now, if I know how to move in order to go to a particular direction, then let's assume that my target is sitting up here. All what I have to do is just keep moving until I hit the target. That means I always go in a direction which is the direct line between my current end effector position and the target. Input. The Jacobian depends on theta and changes all the time. So that's basically it. It's kind of a it's a matrix which non-linearly depends on theta. I don't want to call it a non-linear matrix. That makes no sense. Okay? That means you cannot just say, oh, I'm here, and I take one Jacobian and keep on moving in this direction, hope to get there. That's not going to happen, since after just doing a small little step, this Jacobian is not valid anymore. So you have to recompute it all the time. But that already gets you the idea. So if I now chop this into little pieces and do tiny little steps, my Jacobian is roughly okay for every tiny little step, and I recompute the Jacobian and how to get there, and I can step towards it. And you can also think about this from a discretization point of view. You can think of, I can make a little delta x, which is related to j of theta times a little delta theta. If you want to just do position steps. And all that I now omitted is that this here has to be divided by a delta t. And then we're back in velocity land. Okay, but the delta t I can just the deltas have to be small, otherwise it's not going to work. In general, if you now want to solve for theta dot, now we're going and connecting a little bit to your homework. We get j minus 1. Actually, to be proper, let's call it j hash times x dot, where this is some kind of an inverse. And people like to use hash or they like to use daggers, which simply means it's not most likely a simple inverse operator. My little, if I had a two-joint arm, then I have a two-joint, a 2D space which relates to a 2 degree of freedom joint space. It would be a square matrix, and the inverse would be fine. Now we're connecting to questions on the homework. Okay? This is something which I can potentially normally invert unless there's some algebraic problems with a 2x2 matrix, and I get a simple inverse. But here I have, for instance, 3 degrees of freedom and only a 2D space. So what does my Jacobian look like? Well, if I look at this x dot equals something, so this something needs to look like, here's 2 dimensions, and then it has to be 1, 2, 3 components there, multiplying a theta dot, which is a 3 vector. Otherwise, it's not going to work. Now we go and have a non-square matrix which we have to invert, and we have to use one of our pseudo-inverses. So that is essentially, you will see this a couple of times. So today we will basically work with one particular pseudo-inverse all the time, which is the, what is it actually? The right pseudo-inverse. Let's get the right inverse. You'll see more. Good. So let's see what the properties, what all the good things are on the slide. I never know what's on the slides anymore. So that holds essentially only for small steps or low velocity or small. Small velocities is a small step, or you chop it into many little pieces. That's another way to make small steps. Okay, makes sense. So if you put this on a computer, you gotta ensure that maybe you don't make more than a 1 centimeter step in a human-sized robot. If you have a tiny little midget robot, well, you may have to make millimeter steps. Interesting. A local solution that may be globally inappropriate. What this thing is doing is actually what is called an iterative local solution to reaching the goal. And I can give you a very simple example where it doesn't work. Let's assume you have a robot arm which is currently in this configuration, and I ask you to move over here to the target. And you will actually figure out that most likely at this point, you can only reach down to here anymore. That means I can actually not realize the direct path to go there. Indeed, the robot has to intersect itself, which for some robots is totally impossible. The only way to properly do this would actually to swing around and get over there. Now, this is a absolutely non-shortest path, okay? And that is not being found by these iterative solutions. That can only be found by some global search methods. There's a whole topic about global solutions to inverse kinematics, which often very quickly goes into sampling in kind of AI-style planning methods with A-star-like algorithms, in case you've heard of that, and things like that. Not going into that. That's more an AI topic, and this is a search topic, and we don't want to go there. We just do what's mostly done in robotics. Problems with singular postures. So when we do this inversion, in the end, in every pseudo-inverse, remember, there is an inversion inside. In this particular world which we live right now in, we usually have something like the pseudo-inverse looks like J transpose times J transpose. Is that correct? Minus 1? I hope so. We'll see it on the next slide. So we need to invert this matrix here, okay? And that can still be wrong. It may still sometimes not work. And that happens, for instance, when you solidly, I think what is assumed at this moment, what people say is that the matrix you're having has a rank. So if you have a two-dimensional space, x1, I make it x and y, equals, this is my Jacobian, and this here is my theta 1, theta 2, theta 3. We assume that this Jacobian has at least rank 2. But it can happen that it does not have rank 2. And that happens essentially when in our previous example, again, go back to this 3-degree of freedom system here, when they all start aligning, then you get into trouble with that. And so you actually do have to worry about singularity. So but in this posture, what is the direction in which you can't move? Any idea? It's simple. We all, not just two of us, we all agree we can move in this direction, no sweat. How about in this direction? It's not possible. At this moment, it's not possible since you're all stretched. You're rigid as a rock, so you lose 1 degree of freedom. Actually, you currently only live in a one-dimensional space. The only motion you can do is in this direction. In order to move in this direction, you would first have to move in this direction, and then you start to have degrees of freedom which can move in and out. But you can never move beyond this point since it's here fully stretched. But even if you want to move inward, which is your normal workspace, you first have to move out, and then you can go down. Okay, and this is when you get algebraic singularities. There's one thing which is really important, which is kind of weird. Linear algebra sucks. Okay? I don't know how to express this differently. There's something which is, for us humans, that is totally natural. We never think, do you think about that when I go here, that I cannot go this way? It would never come to us. And somehow, with our linear algebra, we create all these matrix inversion problems, which are just a solid pain in the rear end. And they're artificial. We make them up. So this is weird. If you would go to a machine learning approach and do this totally differently, you can avoid this altogether. But if you go into this analytical or differential solution world, we create these algebraic problems which are physically not really existing. Kind of weird. This is where actually optimization, so QP, convex optimization problems, quadratic programming problems, can help you circumventing these things. But it's kind of an annoying thing that we live in this world where we use algebra and then we basically create mathematical methods which gives us problems to solve things which are physically obvious how to solve. This disconnection between physics and algebra, you find this in robotics quite often. Good. Fine. Just to mention, how can you use inverse kinematics? There's two ways. You could actually do this as an online method. It means you compute one tiny little step, go forward, another little step, go forward, another step, go forward, and you execute it all the time. And that basically means you're really online, just you do one computation, one step forward, you recompute where you are, where's the target, another step forward, keep on going, keep on going. Or you could basically do it everything in a quote-unquote simulation, in a mental model. You just basically iterate until you reach the goal, you read out what are my final joint space parameters, and then go there. So what is the difference between the two things? Just let me make this clear. It's kind of useful to know. So let me get this nicely here. I want to go to this point. And we would agree that somehow the arm in the end may look like this. Okay, make it up. Now, if I do this method where I do step by step, I will make my end effector go here. And basically, every time I come delta x, create a delta theta. Delta x creates a delta theta. Delta theta I realize with some kind of PD control in joint space. Very simple at this moment. Okay. The other method, basically, I create first my theta start vector and then my theta end vector. And I just iterate in simulation until I figure out some theta end. What I can do now, I can basically say, oh no, I want to go the shortest path in joint space to go to theta end. Just basically put in theta end as a target for your PD controller. It will not be a pretty movement. The difference is basically that when you do a joint space movement, you usually do a curved movement. It will most likely go like this. So that a straight line joint space movement does not translate into a straight line end effector movement. If you do a straight line end effector movement, it does not translate into a straight line joint space movement. Weird? I can show it to you. I'm a robot. You figure that out yet? Very advanced. Arm, my arm. Look at it. Cool. So it moves to this target on a straight line. Now, I have all your attention. That's very cool. I move my elbow. Look at my elbow. It flexes, becomes smaller, smaller. Now it stretches again. Okay, we agreed that was not a continuously straight line change in my elbow. My elbow basically became less and then more again. So that's not a straight path in elbow angle space. It was not like my elbow angle was going from a minimal value to a maximal value or vice versa. But my path in end effector space was beautiful. Now I can do the same thing and give you a straight path in joint angle space. That would look like this. And you can actually see that I have this curved movement now in end effector space. Do we care? Well, depends. See, if you had the misery of life, that this here is actually some narrow path where you have to go with a pen through, then that curved path will just run you into the obstacle. And the straight path won't. Other than if space is free, who cares? So this is essentially now up to you to figure out. Now, interestingly, the humans have the tendency to move on straight lines in visual, that means external space. This movement which I showed you has been actually examined by psychologists. You start here, you say, what do people do? Do they do this or do they do this? And they go straight path, which is essentially energetically stupid. Since going in and out with my arms takes way more energy than doing it just a kind of more what's called a ballistic movement where I just go minimally and flow to go to the target. So these are choices you will have to make at some point if you want a robot to do something useful. And I can tell you one thing, there's no choice which is correct. There's only a choice which is appropriate for the current situation. Correct, I mean the correct in general. Yes?
So if we want to make it like a straight path, actually like split the steps in those small pieces.
And go along that little, do one step at a time and realize it with a robot.
But if we just go
if you compute everything beforehand, then you only have the start, the end joint angle configuration. That doesn't tell you how to go on a straight line in end effector space to the target. Okay? So different, again, It's sometimes nice to just compute everything in simulation and execute it in a particular way. It may be energetically better, but it may be workspace-wise inappropriate. You notice this is the fun thing. We go this back and forth, workspace, George space, workspace, George space. It's a pain. There's also people, there's a whole branch of people in AI who work basically, what does it mean to map an obstacle in Cartesian space into joint space, is often called configuration space. This looks like crazy. You know, the space they occupy in joint space is convoluted, miserable, and ugh, don't even want to look at it. All right, so how are we doing time-wise? We have now two things. So I should mention, okay, this method which we're currently using has been termed resolved motion rate control in robotics. Now, why? You know, the guy was on steroids. I have no idea, but it's just a name you will see occasionally. You can also simply call it differential inverse kinematics, and we'll do a good job as well. We need the Jacobian. Now we go a little bit into the annoying parts of how to compute stuff. So this was our forward or direct kinematics. This is differentiation. And the interesting thing is Jacobians have, now let me get some space again here. Look, our x vector, we mentioned that briefly at the end of the last lecture, has actually a couple of components. It has an x1, x2, x3, let's say 3 Cartesian coordinates, and then it may have an alpha, beta, gamma for orientations. Since that's potentially all what you want to control. It's not just going for a point with a coffee cup, you want to keep it straight. Now, and thus, the Jacobian basically needs to have something like 1, 2, 3 rows for positions and 1, 2, 3 rows for orientations. I will spare you in this course as much as possible with orientations, since they are a pain to work with. Much too much work most of the time. Getting the Jacobian components with respect to positions is actually straightforward. So if you just differentiate, literally, we know how to write down with homogeneous transformation matrices, for instance, our Jacobian, our transformation from world to any vector space. But not our Jacobian, sorry, our function f. It's just a multiplication of homogeneous transformation matrices. When you do this differentiation, you get these first two rows. Now, interesting, if you do the differentiation with respect to orientation, now you get into the trouble of did you use fixed angles, Euler angles, or whatsoever. You can do the differentiation. Remember, we have in the homogeneous transformation matrices, we have the big R, and we have the offset vector, let's call it O, and we have 0, 0, 0, 1, 0. And here we have angles, joint angles in there, or something, orientation angles. And we have, well, these R's are based potentially on some Euler or fixed angle, and the offset vector is normal, not a big problem. So, if you do this differentiation properly with respect to all these variables, you get what is called the analytical Jacobian. Okay? And this is fine. It's a decent Jacobian. You can work with it, and it's a useful thing to do. But it depends on those fixed angle, Euler angle conventions. It turns out there is another one, another Jacobian, which is called the geometric Jacobian, which is much easier to work with because it doesn't have the problem of what did you do first and a Euler angle, which sequence of angles did you use in order to rotate through the world. And that's what we usually use. And let me tell you about this thing. For that, I have to create a plot. Do I have this nice? Good. So we have a robot arm, which basically has multiple joints, 1, 2, 3, for instance. We have a final point P at the end of the robot. And that works in 3D now, without, I just put it into 2D. And what else do we have? We call all intermediate points. This here would now be pi minus 1. This here would be pi minus 2, for instance. And we call the joint axis for every of those degrees of freedom. So that would be the I minus 1 degree of freedom, for instance, in this notation. And it has also a zi minus 1. It has a zi minus 2. Okay. Just making up the notation. So there might be other stuff in between. Good. Now figuring out how every degree of freedom can contribute to the motion at the end effector is equivalent, as it turns out, to figuring out what is called the geometric Jacobian. That's a nice, easy thing to think about. So let's take, for instance, this degree of freedom down here. How, now freeze this one and this one, okay? They are stiff now, forget about them. If I move this guy, how can this point move? Well, it's very easy to figure out. So we just create a approximately straight line, as much as I can do this, between this point and this point. And then I know this can essentially, if I move this degree of freedom, it can only move in this direction. Okay? Make sense? Not a big deal. Cool. Now, how can I express that direction? Well, it's actually very nice. It's basically the P, that was my point P here, minus the appropriate point which I've just been using. So in general, call it pi minus 1 or whatever you want to call it. And so this is basically this vector here. And direction of motion comes from the joint axis. So this would here my joint axis for this particular degree of freedom. And what I'm going to do is the outer product. So stick my finger into the direction of the joint axis, stick my other finger into the direction of P minus pi minus 1, this, and I know a positive motion around this joint axis will give me a motion in this direction. Make sense? And that works in 3D. That's the nice thing about the cross product. Despite I just show it to you in 2D. Cool. Yes?
Could you please explain the P minus pi minus 1 part?
Pi minus 1 is any point somewhere, any other degree of freedom different from the end effector. Any. So I basically just made it up here. Let's assume there's a whole bunch more in between. I call this one pi minus 1, pi minus 2. Now this might be pi minus 3. I could also give them fixed numbers like P5, P6, whatever. But essentially what you're getting is that having this convention, this z, which is a unit vector, rotation axis or joint axis, and that difference from this joint to the end effector allows you with a simple cross product to determine its line of action. And this turns out to be exactly the rho in the Jacobian which you need for this degree of freedom. Rho, column, sorry. Column. Let's make this clear. Here's the Jacobian. In general, if for one end effector, it would have 1, 2, 3, 4, 5, 6 entries. And basically, this here corresponds to position, 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 orientation, orientation, orientation. Now that looks terrible. And the first one corresponds normally to a degree of freedom number 1. The next column here is degree of freedom number 2. Let's call it 2, etc. Until we are to all degrees of freedom. So what I'm basically just showed you is how to compute the part of the Jacobian for a revolute joint for the position component. So I basically said, I computed these three things for us. Let's call it joint number 2. And for the orientation, it is just the rotation axis that you have to put in here. Okay? So that actually becomes a very easy recipe how to create a Jacobian without doing massive differentiation at all. None of the stuff which we had to do for an analytical Jacobian is left. We just basically do purely based on our knowledge, where are these points of the intermediate joints and what is their rotation axis in space. This is where your knowledge about coordinate transformation becomes critically important. And this allows you can compute each of those joint axes with the help of your homogeneous transformations in the world coordinate system. And you can also compute the position of each of these points in the world coordinate system, and then you can do these computations. So it's actually not so complicated. You just have to sit down for a couple of hours and do it and program it, and it becomes like an automatic procedure. Not too bad. There's a similar recipe for a prismatic joint. A prismatic joint can only move along the z-axis, that's its axis of motion, and it cannot rotate at all. So it turns out creating this Jacobian becomes now a very simple recipe if you have your homogeneous transformation matrices sorted out. And that's it. And no differentiation is necessary, and this is actually the perfect way how to get the Jacobian. Good. Fine. The book explains that also one more time. I'm not sure whether it's page 72 anymore, or whether the newest book has changed. But that's essentially it. Now we have the idea of differential kinematics. We have the idea how to compute the Jacobian from our given knowledge. That's why I pestered you with these coordinate transformations. You need to know them, otherwise you cannot compute the more interesting components. And now we can look at what methods have people come up with for inverse kinematics. And that's what we do in the last like 10, 20 minutes here. So let's go through that. Pause this again. There is actually very cute, super simple method. And it's simply called the Jacobian transpose. So you should be really puzzled or confused by this thing. So, what does this thing say? This method suggests instead of taking the inverse, it uses the Jacobian. Weird. Is it? Or is it not? Well, there is, let me see, I should have, didn't I have to have used to have a graph for that? Ding, ding, yes. Okay. So, the Jacobian transpose, let's define. What is the Jacobian we recall again? Looks like this. And now if you take the Jacobian transpose, it will just look like a matrix like this. So this is the Jacobian transpose. He said in each of the original columns, we have a 6 vector which shows us in which direction essentially the thing can move based on that joint angles. How would its position, the end effector position change, and how would the end effector orientation change? And you have this interesting little 6 vector sitting here everywhere. And now we're multiplying this with this interesting little delta x vector. It means you are now asking, and delta x has first 3 components for position in the direction you want to go, and 3 positions in orientation you want to go. So now we're projecting essentially this delta x vector with an inner product onto the effective motion which that degree of freedom can contribute. Not such a stupid idea. And that basically says, okay, if I do this, and then I say, do joint number 1, move it this way a little bit, then this is going to be a valid movement towards the goal. It's an inner product between, and let's make this simpler. Let's just forget about the orientations, which are always abstract. So here is my axis in which I can move for a moment. So let's call the, I don't know, call this the Jacobian of maybe degree number 1 in just position direction. Okay, and here is my delta x, in which I would like to move. And I know this here is going to be a unit vector, so it's not just projected down here, and then basically move in this direction a little bit. Okay, so that will basically create, this joint will create a motion in this direction, which will, however, get me closer to the goal. But you see one thing which is weird, okay? It's not going a straight path. It's pointing up. So it going actually only that tiny bit in the correct direction, but it's pointing up. So what you can imagine, you can do this recipe of the Jacobian transpose. Now going back a little bit to, the math here. This Jacobian transpose is a method which gets you at every step you take, every delta, closer to the goal, but in a weird way. What actually is going to happen from a robot point of view, this picture, and here's your target, you usually move in a way which looks like this, some bizarre curved path if you follow that. You will get to the goal, since the Jacobian transpose with this inner product always promises you that you will make some progress towards the goal, just not the directed path. So it's like, you want to go to downtown and you go through, I don't know, Griffith Park. So it's a little bit of a detour. But you will get there.
So it tries to make the path smoother?
It has nothing with smooth to do. It just follows a particular, basically, projection. What we actually do, we will see in a second, it's kind of a gradient descent method where we go down a gradient. But it's not the shortest path to the goal. Old story. If you have all gradient methods, if you have a very complicated valley, so one valley, this is very steep hills, and these are very shallow hills, as your typical valley. And you are here, and you want to go to the goal here. The steepest descent goes down here. The shortest path goes this way. So following the steepest descent is not always the shortest path, and that's essentially what this thing does. So the interesting thing, if you basically look at it, how can you come up with this? The Jacobian transpose, if you just create a cost function, we call it now S. And here's our target, and here's our current position, okay? And we want to square that, so we basically take the transpose and multiply it by itself. That's essentially like taking the square. Makes sense? Inner product of a vector is a squared vector. So it's just the square norm of the vector. So next thing, you fill in f of theta for x. That's basically where we know where we are. And now you do a differentiation of df with respect to theta. Okay, that is going to be the delta theta, that's the gradient. We do multiply with a small constant alpha, so that we do a tiny little step towards downhill only, and call this delta theta. You take the negative, you want to minimize this cost function, so you have to go downhill. You don't want to go uphill. The gradient points the steepest direction up, and we want to go down. And then you just do the math, okay? You do df with respect to theta, put this all in, multiply it out, and you end up exactly with the Jacobian transpose method. So the Jacobian transpose turns out to be the gradient towards the goal. But it suffers from exactly this little problem that it will go not necessarily a straight path to the goal. But the good thing is it's super easy to implement. So you don't even have to invert a matrix. It doesn't help you with singularities. So what's going to happen? So fine, we don't get algebraic problems. If we have this example here, robot being stretched all the way out, and you want to go down here, there will be no gradient. It will just be 0, and you will be stuck forever after. Okay? So there's just the gradient in this direction doesn't exist. There's only one in this direction. Projection down there doesn't exist. And so you will have just 0, 0, because you're multiplying two orthogonal vectors with an inner product.
So it's a local minimum.
That you can call a local minimum. Yes, absolutely. So it's not going to help you with getting to the goal or whatsoever in a better way, except you don't get a matrix inversion problem. Okay, so this is just basically using the picture again, theta 1, theta 2, theta true. These are the different contributions that every angle, joint angle, can contribute to moving the end effector, and then basically this gets put together and you move towards the target in general. So let's go to the pseudo-inverse, our good old friend. So this is the right pseudo-inverse. Now we basically, that's just based on the matrix shape. It's a matrix which has more columns than rows. And the pseudo-inverse just looks like this. You've seen that now many times, also in your homework. And what is interesting now, this is the shortest path in configuration space. So this will basically try to take you to a target Let me draw this, and I have the nicest picture as well. Slides. If I'm here and I want to go there, let me get rid of this here as well. It's trying, the pseudo-inverse is going to try to create a solution which minimizes the amount of movement in the joints in order to get there. So that actually now becomes interesting, since that basically says that that's a principle which you're going to use for your robot. So minimal joint movement in order to accomplish my ineffective goal, which is a potentially useful thing to do, since that kind of saves energy. And I'll show you in a second how this is derived. There are problems with that, as you will see in a few minutes. And one thing is, like, let's assume you have a very friendly brother or sister, nasty brother in both cases. And they twist your arm like this. Okay? Now I'm in this configuration for whatever reasons, and I want to reach here. Now, the shortest path in joint space to reach there would be actually to stay in that kind of spastic posture forever after. That's stupid, so I want to be like this. Thank you. So we need to actually do something about this in a second. So basically doing always the shortest path in joint space may be weird. There's actually another thing which is, hopefully it's, yes, mentioned here, non-conservative. What is interesting in inverse kinematic solutions, which people basically use as a little benchmark, is what happens if you move on a circle. After one round on the circle, is your arm in the same posture again, or is it in a different posture? If you use the pseudo-inverse as is, actually your posture will change all the time. You rarely ever come back to the same posture. That is because it always tries to do a minimal movement, and there's nothing which guarantees that after one full circle, the original posture where you started was the right posture over that path minimization. That is basically what people call non-conservative. You don't also, the joint angle configurations you're using, you only know they're as close as possible to the previous time step, but you don't know exactly what's going. What is nice is it does really a direct, basically it does a straight path in any effective space to the target. That's what all the inversion methods do. Only the Jacobian transpose doesn't do this. You can derive this pseudo-inverse method, again, from an optimization point of view. And I just mentioned that I don't go through all the details all the time. It's annoying. But if you take a cost function, which again, what does it say? It says delta x minus, this is basically a constraint. This is the constraint of the differential kinematics, which says we need to guarantee that delta x equals Jacobian times delta theta. That's differential kinematics constraint. And constraints in optimization we put in with Lagrange multipliers. This is what those lambdas are, in case you remember. They're just basically a way of formulating constraints, hard constraints in an optimization problem. And I take a cost where you say at every moment of time, I want to minimize my delta theta, the shortest step in joint space. So that's my new cost function. My cost function says take the shortest step in joint space between in every iteration, but obey the differential kinematics. That's a hard constraint. You cannot violate it. And now you start solving that basically by taking the derivative of f with respect to Lagrange multipliers with respect to delta theta. You do all the math, go through that, and you end up exactly with a pseudo-inverse. So this is just basically now showing you can actually, from an optimization point of view, trivially derive the pseudo-inverse. And now I know what the pseudo-inverse is doing. It's minimizing the step in joint space at every time step while making sure it obeys the differential kinematics. Yes?
Can you explain again what the
Lagrange multipliers. This is a constraint, okay? We must, whatever solution I'm creating, it must obey this equation. That's our differential kinematics. You cannot disobey it. Now, if you go into, that's most likely calculus, at some point you should have learned how to insert hard constraints into an optimization problem. This is done by basically saying delta x minus this has to be 0 all the time. And you enforce that with these Lagrange multipliers, theta and lambda, which you then use basically as an optimization parameter, and you figure out basically how to make sure that lambda basically gets constrained. So you need to look this up if you haven't seen this, just Google Lagrange multipliers. Wikipedia definitely has a page on that, and every simple textbook on optimization will have that. Okay, I will be running out of time. Let me just move progress. Okay, so here's my little picture on this entire story. So what this looks like is like you're moving towards the target, and basically for every step you're doing, you update, but it's like it's pulling you back with a spring to your original posture, where you just the previous posture from your previous time step. So this is like a little bit of a cartoon, how you can think about that. Now, we add another component. So what I mentioned to you, so what is annoying is with the pseudo-inverse, it always biases you towards where you came from, which may not be the right thing if someone twisted your arm. Can we do something can we bias the system towards a desired posture which we care about? And here's how we do that. We basically take again the same, this here is just our little pseudo-inverse from the previous slides. And now we add an additional criterion which looks like this. What the hell is that, you may ask on a good day? And that is what is called, the first part here, this is what is called a null space projector. Linear algebra, I told you it's going to haunt you. So, what this says intuitively is this little song and dance which I showed you before. I'm here, okay? I want to reach to this point, but my range space is basically realizing this point. But now I have this big null space in which I can move and do all kinds of little things. If I can express this null space algebraically, then I can make sure that any motion I'm doing can only happen in the null space. By projecting the motion I want to do onto the null space, make sure it's not in the range space. Weird language, huh? Really annoying. Fine, let's make it more explicit. Here's my robot arm. And what I'm now creating is I say, here is my favorite posture. This is where I want to be ideally all the time in my life. It's like this favorite posture, I want to create a spring towards this favorite posture, but I never want to change this. It's going to be for the rest of my life my favorite posture. So this vector of joint angles I call theta 0. My current vector is theta. And I create now a criterion, theta 0 minus theta. So theta 0 is my target in joint space. I want to be there all the time. But, so that means what I want to do is, if possible, I want to move my joint angles towards theta 0, but only as much so that they don't interfere with me moving to the target. So two criteria. Highest criterion is go to the target. Second criterion is stay as close as possible to theta 0. Now, this is what this little guy is doing for you. Now, instead of deriving it, I just verify it for you, because it's fun. Let me verify. Is this thing doing something useful? Direct kinematics, differential direct kinematics is, you have the delta notation, delta x equals j times delta theta. So, now, I compute currently a delta theta, which is supposed to get me a step on a straight line forward towards my target, which is basically this delta x which I'm doing. Again, I'm currently here. Here's my target. And I compute a tiny little delta x to get forward. And there's some stupid robot arm attached to it. All right. Now, let's just basically, if we compute the delta theta according to this recipe, let's see what happens. That's easy to put in. So now we just plug the entire thing there and say basically j times, we have alpha j hash, and delta x is the first term, and then plus j times I minus j hash j times, let's call this, I don't know what I want to call it. Let's call it delta theta 0. There's different semantics to that. That's theta 0. Good. J times j hash. You agree that this should be identity because we're talking about a right inverse, pseudo inverse. So this is identity. So I basically realize now alpha times delta x. That was j times hash. It's correct. So actually, I don't need the alpha. Okay, fine. Let's leave the alpha in there. So that would be, I would have to have an alpha in there as well. That's fine. Let's get rid of the alpha. This makes life easy. Alpha is 1. Always good to set alpha. Good. So we realize delta x. Now what happens here? Well, let's just multiply it out. So j times 1 is j. Then we get minus j hash times j. Okay, j times j hash is our good old identity friend. J minus j is 0. And it turns out this term does not contribute anything in the world of our direction towards the goal. So delta x is not changed. Cool. So we just verify that this particular identity minus j hash j is what people call a null space projector. It takes the vector here, theta 0 minus theta, and projects it into a space which cannot interfere with us moving into delta x direction. So null spaces are good guys. We can actually work with them. We can express them, and we can do linear algebra with them. Horribly abstract maybe, but incredibly cool what you can do. Cool. Now you can basically put this again into an optimization problem. And basically now what you're saying is that you want to basically minimize delta theta plus some difference from the true target. You still have your differential kinematics constraints. You pull this through as an optimization, and you come up exactly with this as a solution. Now that we don't go, so this is too painful. Again, very important. Because we have a system with too many degrees of freedom, it's a redundant system. Whenever we create a solution which somehow makes a decision how to use these degrees of freedom to reach in this lower dimensional space for the target, there has to be some principle behind that, how we choose among the infinite number of possible solutions a particular solution. And all what I try to repeatedly tell you is this most of the time can be grounded in some optimization criterion which actually generated the solution. Which then tells you that, in general, if you can go to optimization, create even more complicated optimization criteria with inequality constraints and other things to create other solutions for inverse kinematics. And this is where basically convex optimization and quadratic programming comes into play. Okay. Now, I'm not going to go through all the other things. There is essentially a whole class of additional things what you can do to do inverse kinematic solution. I just mentioned them to you. It's getting too much, but it's useful to think about it. So, delta x, let me just do this in vectors again. So this is delta x equals some matrix J times delta theta. And we want to get delta theta given a delta x. And the misery of our life in some sense is that this J is not a square matrix. It is a rectangular matrix, which then creates all these Jacobian transpolated pseudo inverses of whatsoever method. Well, no. You don't like something in math, you just fix it. And that's a very good thing to do. So we can just go and fix a little bit. Let's make that J a little bit bigger. Darn thing is simply too small. Here we go. Now I have a square matrix, and I basically do everything fine. Cool, huh? That's brilliant. And that's essentially what you can do. You basically can create additional constraints. Differential kinematics is nothing but a constraint. It just tells you delta x has to be j times delta theta. But why not add some more constraints? They have to be based on delta theta and something which can be computed based on joint angles and some other criterion, and add them in here. And that is actually doable. And you can make up these constraints. One of the methods doing that is what is called the extended Jacobian. And that now makes it clear now that the orange stuff is extending the Jacobian to a bigger system. And people just added additional constraints. And basically what they did, they used this kind of constraint that you want to stay close to a desired posture, for instance. This is like f is the g of theta. So this is just taking the difference between the theta 0 and theta, squaring it up, calling this an additional cost component, and then basically taking the derivative of that and trading based on this constraint in this additional Jacobian space. And if you do this the right way, you can actually convert it and create an inverse kinematic solution. It's just a little bit of a painful method. The interesting thing is this extended Jacobian, which is, I think, the math looks something like this. If you want to derive it, that's not readable, obviously. It is one of the only methods which truly generates what is called a conservative solution. That means you do a circle, and you're guaranteed to come back to the previous posture. Now, the effort you have to do in order to do this may be a little bit too much, since you have to, these columns here, these rows of this matrix come through a singularity composition of the Jacobian, and it's a fair amount of work in order to realize it. The previous method, which I showed you, is just with a null space projector, does actually in general a very good job. You don't have to go through this extra work. But what is important about this is essentially the idea that in order to get additional rows in a non-square matrix, you can create a new criterion, for instance, that you want to have minimize the square distance from a rest posture, differentiate that, put this in the appropriate way into these additional rows of a extended Jacobian, create new constraints, and suddenly you can solve this problem analytically. And that's now up to your genius how you do that. Okay, and essentially the extended Jacobian, the intuition is there's a desired optimization posture which you put in there, and at every moment of time it tries to basically keep your robot arm as close as possible to this optimization posture. This is the same what kind of the null space projection method does it well, just the extended Jacobian does it in a mathematically perfect way. Good. So that's it. That was kind of a quick step through inverse kinematic solutions. Small, important component. Jacobian transpose, super simple. Doesn't go straight to the goal, but very easy to do. All the other ones require matrix inversions and additional work and more linear algebra. In the end, it's not very hard to realize that in like 30, 40 lines of code, depending how you do this. If you use some math packages in C++, like Eigen or something like that, it's actually a very compact coding which you can do. If you write it in standard C with for loops and whatever, you just have to nested loops to the matrix multiplications. It computes very fast. It always gets into trouble when you go into singular postures, and you have to do something about this if you run out of range. And all these methods only create local solutions. So if you want to go from here to there, and there's something like you cannot penetrate through your own arm or something like that, you will simply get stuck. So you cannot use this all the time. Like us humans, most of the time when we reach, we never have these problems of singular postures. It just doesn't occur. Our human arm is quite nicely configured. Some robot arms don't have these nice properties. Okay, thank you very much. Done for today.